Okay, so now we are starting a very interesting and amazing topic, which is advanced distillation, which contains side streams. Sorry. So when you have a distillation tower, I'm going to do something really quick here. Okay. So this drawing is really relevant to be understood if you are studying distillation topics. So this is the basic the basic sketch, let's say. So you have a feed and you will have some distillate here, which is going to contain some amount of the lowest boiling point component here, and some amount, of course, as well of the highest boiling point component. And at the bottom, so this is mass flow, okay, or molar flow, let's say. Okay, but this is the basic case. So here, important to understand that at the top of the column, what you get here is vapor that is going to be a condensate, or partially condensate, or totally condensate in this condensator. And at the bottom, what you will get is a liquid, okay, which is going through a unit of a heating unit, which is going to produce so a, how to say this, let's say a solution or a stream with a higher temperature, and it's going to vaporize, right? So I mean, there are many things we could analyze about this, but what I want to focus on this video is about the side streams. You could have one feed, or maybe 2 feeds, or many more, right? Or you could have as well side streams, like for instance, you are producing some alcohol here, and the main product of the plant is this one, but you are analyzing new market and you need the same alcohol but with a little bit less, you know, like it's not a little bit, but with this concentration. So then you would withdraw this alcohol in a lower boiling point plate or stage of this distillation tower. So what I want to, so usually to calculate the amount of the number of stages and stuff, we use Mackay-Thiele diagram, right, which uses this reference line, which is going to be actually a line, you know, not a curve, a line, perfect line. And let's say ideal case, we don't have any isotopes and stuff. Oh, sorry, it's a little bit of time. Yeah, so what we do is, okay, we have the feed, which is going to be, let's say here, we have the conditions of the distillate, the conditions of the bottom, and then we are going to calculate, knowing as well how is this, how is the input, which could be boiling liquid, could be saturated liquid, sorry, it could be saturated vapor as well. So that depends on the intake factor, which is going to be the negative slope, the negative value, sorry, of liquid over vapor. Okay, liquid over vapor. Or there is another formula for this, which states 1 plus the enthalpy of the boiling liquid minus the enthalpy of the feed, or the enthalpy of the feed over the vaporization enthalpy. This is another formula for getting this slope, this value here. But anyway, so what we are going to do is at the end we are going to have something like this, right? And you can calculate the number of stages. So this is about basic distillation, right? With one input and 2 outputs. But if we have, for instance, more than one input, we are going to have actually something. I'm going to do just a sketch. Sorry if it's not very accurate, but okay, I was saying, sorry, we don't have much time for doing something really accurate. So this is going to be the distillate. So we get to this point, right? To this point, for instance, right here, and then from this point we are going to move here, for instance, and then from this point is, of course, we're going to be at this bottom concentration, and then we can say, of course, it's assuming that we have boiling liquid for both feeds, right? And then we can do the same again, and with this calculation I would say, okay, 1, 2, in the third stage, right? It's the third stage. I will feed the first the first stream, and 3, 4, yeah, in the fourth one at the let me think, it's going to be, yeah, at the bottom of the fifth stage, I would feed the second stream. So these kind of things could be analyzed if we do a little bit more mass and energy balances than before. Just I will explain how it works. So for this deduction of the mathematical formulation of the, let's say, operating line for the second section, which is going to be not as we had before, just we had two sections, rectification section and stripping section. Now we're going to have a rectification section, middle section, and stripping section. So how do we know this equation, this operating line? Because we know this one, we already know that one is the really simple one, which is going to be the reflux ratio was 1 plus xt over b plus 1 as well, right? This is really easy. And as you get here to the feet, then you go just down, and you don't even know to calculate the last one. I mean this operating line for the stripping section. But how do we get the middle section? That's what we are going to do now. So now I'm going to explain the key part, which is going to be, okay, we have a rectification section, and this second section is going to be rectification plus side stream, right? So if we think about what's coming into this, we can tell, okay, some vapor to the rectification section, right? And what's coming out from this, and we need to be careful about this now, because here, of course, is going to be N liquid in the rectification, but as you can see, this N liquid is going to be split into this one and this one. That means if we think about it, we will have N liquid, the rectification is going to be equal to NS plus a term, which is the one we are looking for. What would that be then? Very simple, because it's this term. Okay, that's what we have so far. Then if we do a mass balance around this rectification plus side, we will end up with, okay, be careful here, because it looks like this stream is not leaving, but of course it's leaving the system, right? Because this is a side stream. So we will have this going in, is this one. What's leaving? Of course, the distillate is leaving, the side stream is leaving, and this is leaving as well. This like framework that we're putting here. So if we cancel this out, we will get the following, which is, okay, then we can do a composition balance. We end up with, so basically same as the mass balance here, but now with some composition, some fractions of the composition. So remember that what we want to get is a function of y versus x. So, and here we are going to divide all the terms by NRV, okay? This is what we get, and then we, what do we have here like command? Let's think about it. We have, for instance, an S here, okay, but it's not important. Yeah, so let's leave it just like that. Okay, these two, of course, they are the same, so let's rearrange this. Okay, this is what we have. It looks okay, but what's the issue? For instance, we don't know what this is, and we don't know what this is, right? So we can't measure them because it's inside of the column. So what we are going to use is the concept of reflux ratio. What reflux ratio is? So reflux ratio is nothing than what it's reflux inside of the column, which is going to be this, right? What it's going to be reflux inside of the column over the product. Basically, so reflux over product. Sorry, I'm not writing really properly there. I mean, not really nicely. So basically, this is the reflux from this section that we are working with. Then, so in this case, we need to use a trick. First of all, let's see that this right here is exactly what we have here. Okay, so if we change this, we are going to have y equal to, of course, that's going to be vs times nd plus ns. We can measure them, so it's not a problem. We can measure them, that's fine. NRV, we already got rid of one of the terms we don't like. It's d plus ns, it's s, sorry, it's s, that one is ss. Let me move it a little bit. ss, nd, no, sorry, nrv, right? And now the problem is this one. So in this case, we are going to use a trick, let's say. So we have this reflux ratio, yes, that we define here. Let's put it here, nr minus ns over nd plus ns, right? If we add 1, would be like, I mean, like if you add 2/3 plus 1 is the equivalent to have 3/3, I mean, times 1, so it's same, right? So we are going to add 1, meaning nd plus ns. And what's the beauty of this? We get rid of this, and then we have nrl nd. Let's think about it here in the drawing. What is that? That's nothing than, so let's see what goes here, right? So basically the mass balance we had in the rectifying section, NRV is going to be equal to NLR plus ND, or simply D. Let's say ND because I'm using N. ND, right? What we know here? We have NRL plus ND. NRL plus ND. This is equal to NRV. NR rectification vapors. Yes. ND plus NS. That means this button is nothing than we said this is going to be V plus 1, right? So this button, this term here is nothing than V plus 1, right? Equal to, let me think if I'm doing this correctly, yes. N V R over ND plus NS. So we could simply plug it here. So we get this when we plugged the value for, the expression for the amount of paper going up to the rectifying section. We can cancel this out, and this is what we are going to end up with. Meaning, so we were talking about, so we have this, and the second line is going to be, then we know this point, we know it definitely, it's going to be the intersection between this point and the y-axis, which can be calculated with this part, which is, this is just ms plus d, right? And if we say x is equal to 0, then it's going to be just the intercept, y-intercept. So we know this is this line in general. Of course, it's going to be till certain concentration. It's going to be just this part, and then for the next part we don't actually even need to think about how to get it, but we could again do a mass balance and an energy balance. This case was just mass balance, right? Yeah, mass balance. Yeah, and that's everything I want to share with you in this video. I hope this is helpful for you to understand how to work with side streams. So basically what we just did for one stream is going to work is to work for any side stream, either input or output, inflow or outflow of the equipment or of this distillation tower or any distillation tower, of course. What else I want to point out? There is something else I'm forgetting. Yeah, I just remember, be careful when you put this this boundary, like if you are doing rectification, it's going to be just before the side stream, and if you're doing the rectification plus side stream, put this boundary, this control volume, just right after the side stream. Yeah, that's everything I wanted to tell you. So have a wonderful day.